I started using them. I kind of like them. These videos, probably not. If I can find a way to link to this video, absolutely. But it's in another textbook, so it's copyrighted, and I don't think there's a way I could put a link to it. But I do have links to other videos that show you how to work the problems. So, yeah. Okay. So I'm going to go ahead and play. Exactly. If you record the lecture, then you have the video as many times as you want. So, all right. So I'm going to go ahead and play it. Maybe if I can get on the right page. Okay, there I am. All right.
Hello. In this video, you will learn about resonance and formal charge. These tools are part of the Lewis model for chemical bonding. For some molecules, you can write more than one valid Lewis structure. For example, when you write a Lewis structure for O3, ozone, you can write this structure with a double bond on the left, but you can also write this structure, which has a double bond on the right. Both of these structures predict that the ozone molecule has two different kinds of bonds. One single bond, which should be longer, and one double bond, which should be shorter. However, when we look at ozone in nature, we find it has two exactly equivalent bonds. So, how can you represent ozone with the Lewis model? You can use a concept called resonance. Resonance structures are two or more structures that together describe the bonding in a molecule. For example, the resonance structures for ozone look like this. Draw resonance structures with a double arrow between them. The actual structure of the ozone molecule is intermediate between the two resonance structures and is called a resonance hybrid. The term hybrid comes from breeding. The offspring of two different breeds of dogs produces a hybrid dog, one of mixed breed. Similarly, the molecule described by two resonance structures is a hybrid of the two resonance structures. The space-filling model of ozone looks like this. Notice that its bonds are equivalent. These bonds are intermediate in length between a single bond and a double bond, as you would expect from a structure that is intermediate between the two resonance structures. We now turn to the concept of formal charge, a fictitious charge that you can assign to atoms in a Lewis structure to help you distinguish between alternative structures. The formal charge of an atom in a Lewis structure is the charge the atom would have if all bonding electrons were shared equally between the bonded atoms. In other words, formal charge is the calculated charge an atom would have in a molecule if you completely ignore the effects of electronegativity. For example, because fluorine is more electronegative than hydrogen, the electrons in the HF bond are not equally shared. As a result, HF has a dipole moment. The hydrogen atom has a slight positive charge, and the fluorine atom has a slight negative charge. However, the formal charges of hydrogen and fluorine in HF, that is, the charges we would calculate if we ignore their differences in electronegativity, are both exactly zero. The formal charge on an atom in a Lewis structure is the difference between the number of valence electrons of the atom and the number of electrons it owns in the Lewis structure. An atom in a Lewis structure owns all of its lone pair electrons and 1/2 of its bonding electrons. You can calculate formal charge with this equation. Formal charge equals the number of valence electrons minus the sum of the number of lone pair electrons and 1/2 the number of bonding electrons. So, for the hydrogen in HF, you calculate the formal charge as 1 minus the quantity 0 plus 1/2 of 2, which is equal to 0. For fluorine in HF, you calculate the formal charge as 7 minus the quantity 6 plus 1/2 of 2, which is equal to 0. Notice that in a neutral molecule, the formal charges on the atoms total to 0. In polyatomic ions, the formal charge on the atoms sums to the charge on the ion. Here is a practice question for you. What is the formal charge of each atom in this Lewis structure? A, 0, 0, 0. B, plus...
All right, so we'll come back to formal charge. There's one other video that I want to show you on this page that has to do with resonance. See, that's a picture from his video. Let's see. Matter of fact, I think this is the exact same example as the one in our book, which is odd because it's not the same writer. Okay.
In this example, you learn how to write resonance structures. The problem reads, Write the Lewis structure for the nitrate ion. Include resonance structures. Begin by writing the skeletal structure. Since nitrogen is the least electronegative atom, put N in the central position. The skeletal structure then looks like this. The second step is to calculate the total number of electrons for the Lewis structure by summing the number of valence electrons for each atom and adding 1 for the -1 charge. Go ahead and try that yourself now. What is the total number of electrons for the Lewis structure? A, 12, B, 23, or C, 24?
So this one, nitrogen's in group 5, so it has 5 valence electrons. And oxygen's in group 6A, so it has 6. Yeah. So it's 6 times 3 is 18 plus 5. So, all right, so you guys, looks like almost a split between B and C. So we'll go with B.
The correct answer is C, 24. The total number of electrons is equal to the number of valence electrons in nitrogen plus 3 times the number of valence electrons in oxygen plus 1 for the negative charge. Since nitrogen has 5 valence electrons and oxygen has 6, that's equal to 5 plus 3 times 6 plus 1, which equals 24. Now, place 2 bonding electrons between each pair of atoms. Distribute the remaining electrons first to terminal atoms. Notice that you have used all 24 electrons, and there are not enough electrons to complete the octet on the central atom, nitrogen. Complete the octet on nitrogen by forming a double bond. You can do this by moving a lone pair from one of the oxygen atoms into the bonding region with nitrogen. Enclose the structure in brackets and include the charge. Notice that you could have formed the double bond equally well with any of the 3 oxygen atoms. So write all 3 structures as resonance structures and include double-headed arrows between each structure. All 3 resonance structures together specify the structure of the molecule. The actual space-filling molecular model of the nitrate ion is shown here for comparison. Note that all 3 bonds are equal in length.
All right, give me just a second. Let me stop that.
In this example, you learn how to